talking about the event-driven trait. And I've been doing event-driven programming since I actually started doing programming back on a Commodore 64. Actually doing hardware and doing assembly and things in BASIC. I actually built a small robot that actually could take, commands. You would give it commands and it would do actions. And that all was event-driven. I didn't even think about that, for quite some time. And as I learned different languages, I always kind of look back at that. But basically, our world really is event-driven. And here's an example. Breaking news. We see it all the time, right? Breaking news, that's an event. That comes in asynchronously to whatever we're doing. And that's how the world works, right? Life's also an event, event-driven. Each of our phones has, different types of notification systems, right? That's an event. It comes in asynchronously to whatever we're doing, shows all of our personal information to anyone who's looking in a conference room, with your phone facing up, okay? Embarrassing photos from your friends, they get shown, as well as any other type of data that you want to see. So if you start thinking about this, what are the developers out there that are actually doing event-driven development? Well, if you've done any GUI development on Windows, macOS, iOS, JavaScript, in the browser, or even in Node, you're actually doing a lot of event-driven development. Your good UI design is event-driven. And for all the same reasons that, putting services in the back end should actually be event-driven as well. It's the same reasons. Let's think about that for a second. What this really means is that the ones that are doing a lot of event-driven development are web developers. Just think about that. Let that sink in for a moment. The people who are actually doing most of the event-driven development that we have now are actually, doing it with JavaScript, they're doing it with HTML, they're doing it with CSS, they're doing it with all these different technologies. And basically, it's still done poorly. And let's take a look at some of the examples. How many of you like modal dialogues? You don't count, Dean. Blocking SQL queries. Who puts a blocking SQL query inside of actually handling something? Yeah, we all do, right? Logging. Who puts logging within their functions? When an event comes in, they log the event, right? Always happens. What about RPC? REST. So REST calls? Anyone? Yeah, we do that. Anyone know what long polling is? Okay, well, we'll talk a little bit more about long polling and why it's bad. There are actually applications out there that get billions of dollars, and every click of the mouse on that UI is a blocking REST call. I'm not joking. I wish I was, but. And most of them exist in, the kind of large organizations that you usually do. In the messaging space, we also have something else, which is a pure evil thing. It's called Synchronous Agging Jms. When you use JMS, a lot of times when you send an acknowledgement, you do it in a blocking fashion, so that you know from the application of a receiver that it actually got that message. It's an ACK of an ACK, but you need an ACK of an ACK of an ACK, and an ACK and an ACK and an ACK. These are kind of broken, right? And all this blocking, really broken, and all this blocking actually is very detrimental to what we do. Let's think about the term event-driven. We're driven by events, right? We're driven by data coming into us. When you're doing these type of development, there's a natural model that kind of speaks out to this. State machines, right? Moving from one state to another. And we'll talk a little bit more about that. But the idea of being driven by events and events coming in is not new. We see it all the time. Networking is where my background is, protocol development. And protocol development is all about an event, in that case, a message or a packet or a frame coming in, processing it, and doing something else. A lot of times sending another one, but not all the time. So how you react to it. So event-driven development and event-driven designs are all about reactivity. Another thing, asynchrony. Asynchrony is about doing something, being able to do something else, and then a result appears. Okay, that's one idea, but there's another one too. Asynchronously, meaning that events can happen while you're processing other events, that asynchronous nature. Decoupling. Decoupling is something that we talk about a lot as if it were, the magic thing that we want to strive for. And in many ways, we do want to decouple systems as much as possible. It's really about the dependency. The dependencies that matter are the ones that where the dependency comes into play only when you need something specific. Think about compilation, right? if your dependency happens when you are executing something, that's actually easier. If you never have to hit it, you never have to hit it, right? Lazy binding. This is basically taking these same concepts and making them to a larger system as opposed to just a small piece of software is actually very advantageous. By decoupling larger pieces of a system and then decoupling those smaller pieces and then decoupling even the smaller pieces from that, what we do is we get things which are much more composable. Okay? We've all seen this. We've all done this. And it's my belief that networking and a lot of the things from networking, especially protocol development, speaks really well here because they are the same problems and they've been solved by actually forcibly pulling these systems apart, by looking at what is on the wire, that contract that's there, that binary contract, and then being able to basically assemble these pieces because they follow that contract. So what's the opposite of decoupling? It's coupling and also synchrony. When we have things which are very tightly coupled and they're very synchronous, this is why we can't have nice things. It really is, it does lend itself to the point that when these things are tightly coupled, we can't tease them apart, we can't really service them and compose them however we want. I would kind of draw an analogy to, if you've ever seen stickers like it says, no user serviceable parts inside. That's actually what a lot of synchronous, coupled systems look like. You can't pull them apart. They may have nice, tremendously nice abstractions, great object graphs, everything else, but you can't pull them apart and just compose them however you want. And that's really a problem. So I apologize the slides being a little dark, but hope you can see this. So I've done this. We've all done things like this. Here's a little bit of code. And since it's kind of hard to read, I'll kind of let you go and sort of explain. This is just basically an example of when someone says, but my code doesn't block. Okay, my code doesn't block. It's not doing anything blocking. Sometimes the blocking is kind of hard to see. So the first thing here is, you're calling logging some event that has happened. Well, in the comments here is that the appender goes to console only, so it won't block, right? Well, that's a fallacy, right? If you're writing to the console, it's going to block. It may not block in certain other ways, but in others it may. The other thing is here is just a try-lock loop around with a while loop doing some condition. And the comment here is literally a comment that I found in a piece of code that I was working on with someone a long time ago. And it's, it won't block since we're just trying. It's log-free. Woot. I mean, that's great. But too bad it's not right. And the nice thing is, with Java, with Java 7, you can actually pull that out into, try with resources. So we'll make sure it gets freed, when we're doing that as well. Last one, I've seen this one many times, where you grab something from a database and you think it's a local file, so obviously it's not going to block. Well, disks are slow, so you're always blocking. So, don't do this. Stop being bad. Realize that what you're doing can block or will block, as opposed to thinking that we're kind of wishing it away. Blocking has its place, but it has some serious limitations. And sort of look at this. Let's take a look at what a normal kind of blocking RPC or REST call looks like. You send a request, there's some processing, and you get a response. The first thing is you have delay that is initiated by sending that request. It takes time for that to actually get somewhere. Once it's gotten there, it has to be processed, and it has to generate a response, and that response has to travel back. So what happens while you're waiting? This behavior is called stop and wait. If you think about it from a flow control perspective, you send, you wait, something comes back, and then you can do that again. Send and wait, something comes back. While you're doing that, nothing happens. You're blocked on it. Now, other designs that are asynchronous, you can do something else while you're waiting on that response. But a lot of times when you implement this and you're using it, like using most REST calls, how many of you are actually doing something else while you're waiting for a REST call response? Yeah. Some do, some don't. But, how bad is this? Well, this is a serialization point. And what that means, and we've seen, is that Amdahl will come into play. Amdahl's law will come into play, and it will basically start to hunt you down. But the question is, does it hunt you down like Chuck Norris? or maybe it's like Jack Bauer. There's quite a difference in that. My contention is that, that it actually is more like this guy, tracking you across the universe just so they can freeze you in carbonite. And think about that, right? The speed up that you're going to get, the theoretical maximum speed up that you're going to get, is a function of basically how much serialization you have. Even a small amount. 5% is a very small amount. And having just that limits your scaling, no matter how much, how many processors you throw at it. What this means is you can't just throw hardware at the problem. You sometimes have to think about how can we reduce that serialization. You have to think about it from the architectural perspective. You have to think about it from the actual systems perspective as well. You have to think about it from several. So when you talk about this and you start thinking about it, there's lots of additional reasons why people say that blocking is easy. And one of the ones that I've seen over and over again is that blocking makes error handling easy. Oh, really? Well, Joe had some wonderful thoughts about how to handle errors asynchronously and off to the side. And that's actually how most protocols work. They handle errors out of band. And there's a lot of different examples of this. One one non-example of this would be the way that TCP does a reset. It actually is sent in band, kind of. But it still is at asynchronous. It does not live within the data stream. So again, this is a piece of code that shall remain nameless, but this is an example of the kind of lengths that enterprise software goes to provide a very well thought out set of error conditions. Now, I'm not trying to pick on exceptions here because obviously with Java 7 you can pull that that out of there and you can get rid of that finally block because that was really causing us problems, right? So with Java 7 most of that gets cleaned up. But just so you know that I'm not just picking on Java, I'm also going to pick on C a little bit. If you've ever looked at a kernel like the Linux kernel, you'll notice that there is a consistent way that kernel developers tend to handle errors. They tend to go to fail, right? You go to a failure section within a call, you do some cleanup, because really you're responsible, right? So you're going to be doing some cleanup there, and then you return out of that with an error condition. And if you compose this way, it gets a little easier. That's the hope, at least. But also there's error handling really has nothing to do with blocking. It really does have everything to do with how you handle errors, the thought that you give to the error handling structure. So saying that using blocking calls because it's easier to handle errors is really just doesn't make a whole lot of sense, does it? No. So just so we know, what you want to do here is you don't want to forget these little curly braces, and you don't want to do go to fail, like Apple. So. Just to make sure that we cover all of our bases here. Says the guy holding an iPhone and with a Mac. But I mentioned this earlier, state machines. State machines really do rock. And it's not just because I'm a hardware engineer or originally was trained as one, although that's what I'll say. If we start looking at what a state machine really looks like, I wanted to cover this real quick. The difference between edge-triggered and level-triggered. And a level-triggered system, you're in a current state, you have some transition, and that's where your edge comes into play. That just happened. And then you have the other state that you're in. And the edge-triggered and the different level-triggered. And basically you have a state transition. Is it pulsed or not? The different conditions. There's many different ways that a state machine can kind of work. And that's kind of a nice thing. We've developed these over quite a long period of time, and they actually are pretty tried and true models that do scale pretty well. So, but you can implement these things in software a lot of different ways. Transition tables. How many of you have heard of what a transition table looks like? Okay. Yeah, the idea is very similar to basically a graph table. Okay, you have current state, event, next state. And you can look at that transition table and tell all three of those things, what state you're in, what event comes in, and what state you go to. Those are three very important things. We'll come back to those here in a minute. But you can also do this with Java enums. Enums with methods are something that I only learned about fairly recently. I've been doing Java for really only a small period of time. But Java enums are actually really nice and elegant for composing these things in a very nice, pretty fashion, actually. I've also played around with JavaScript prototypes, using those to hold actually state. And all those methods, those three methods allow you to actually compose it so that you can see in one glance current state, event, and next state. Another one that's kind of nice, and we now have it in Java, we didn't have it for a while, is being able to actually use a table, but a table of lambdas, okay, so that you can put all your, you not only see the events, but you can also see then the methods that would be called and how the processing would look. And that's kind of nice. It does get a little bit hairier, especially if those lambdas are anything that's complex. A lot of times they shouldn't be, but we do. All of these, I'm not going to tell you which way is the best way to do it. All I'm going to tell you is that as long as you follow some, another thing that I want to mention here, it doesn't really matter what you use. Okay, it's personal preference. So let's take a look at what I do. What I do is basically a switch case. On event, switch on the current state, set the new state. And that's because at all those places, I can see the event, I can see my current state, and I can see my next state. I don't try to hide this. After doing several different complex state machines and actually having to debug when certain events occur and why they've occurred, not having those three pieces of information has screwed me up royally. So I like to have all three of those in my face. It is not the best practice to have them in a switch case for performance reasons, so you have to think about that up front. But any abstraction that allows you to see those three things and doesn't hide it is a good thing. And as Martin mentioned, make them observable. Okay, make it so that you can observe them from outside of that running process, or that running thread, or that running component. Very, very, very nice. So it's great that state machines are out there. They've been tried and true in hardware design for as long as it's been around. But I also wanted to mention that state machines are one of the most testable entities there are. Okay, there's two things that you want to think about. Does my code implement it correctly? Okay, that's a fidelity issue. Okay, I have a design. If it's being implemented, is the implementation, does it have high fidelity to what it should be? And there are techniques that allow us to do that. VLSI testing techniques. VLSI testing is all about this. It is all about making sure that the design and what gets implemented are actually in fidelity with one another, up to a certain point. So there's been testing techniques in ARC or branch testing that have evolved to basically take a set of logic inputs and generate a test array, which is a minimal test that you have to satisfy. So imagine, if you will, instead of code coverage where you test every single line or try to, think about if you can test every branch, okay? These are direct analogs, and people have looked at actually taking those techniques and porting them. Some have been a bit more successful than others. But that step is actually very important and can be done with state machines much easier than it can be with any other type of sort of logic. And certainly easier than certain types of data structures. The second thing is the design of the state machine, is it safe, is it correct, and is it provably verifiable? Well, there's a great thing called SPIN. SPIN is a model checker. It can explore millions of states, billions of states, really, and to do different types of predicates that are on that state machine. You have a tool that is there, and oh, by the way, in 2002, it won the ACM System Software Award. It's been used on NASA systems. It's been used on, including Cassini and a whole bunch of other things, even up to Mars Lander, to verify certain properties within state machines. There are certain properties that even in simple state machines you may think about, but proving that they are is a hard thing to do. So if you do anything with non-trivial state machines, you're probably going to want to look at something like SPIN, just to make sure that what you're thinking of is going to be safe and not halt and continue and things like that. But it's the same kind of problems that we normally have, even without state machines. These are well understood. Now I want to show you a couple examples of some state machines. Some of these are serious, some of them aren't. So the first one, everyone knows this one, right? This is one that Martin had, and this is the TCP State Diagram. We go through it all the time. You go from close to listen, send, received, established. Or if you were to be in just the right situation, you go from, to send, to listen and then send, send, and established, right? You have these top states here. What's the bottom states? Well, the one off to the right, is what we call a passive closer, okay? This is a passive close, the person who is being closed upon, okay? They have two states. They go into one, they transitioned into the next. The other thing, which I've sort of circled and have a question mark around, is this is called the active closing state. It is a mess. It still works. It's very resilient. Most of the transitions out of it are not shown here. It still works. It's very resilient. It's not designed well. There are certain things that could make it better. There are certain problems that can't be represented in it, but can actually be gotten out of it by the state transitions. So, sometimes you put something together, it works, and it works fairly well, although it's not pretty. Here's one that's on the opposite scale of extremely ugly. It's mostly a flow chart, and this is really what some state machines end up looking like. Okay? If you design a state machine and you start thinking, oh, I have to model that transition not as an edge, but actually as a level, and now it has to have its own state, so you add another state and you find out that there's a hot path through things, so things look kind of like this. And the reason why this is really ugly is because of that thing, whatever that is. That's what things typically tend to look like. But then trying to bring them down into something is an exercise in trying to redesign and trying to know what's going on there. I'm glad you can't see the rest of it there. It's pretty hideous. Here's a very elegant state machine. We use these all the time. This is the cache coherency states for Intel processors. This is the simplified version. This is messy. And there's a couple things to notice about this. There's a large amount of symmetry. There's also a large amount of transitions which go back to the same state. Every one aside from I has them. And there's reasons for this. This is works very well, and it's extremely resilient. It's a very well-designed type of state machine. Typically, when you look at hardware state machine designs, they are all very resilient, very consistent, and they work very, very well. So, any questions so far?
I have a question.
Yes.
Do you ever generate the code from state machine descriptions?
Yes, I have done that. And it does work fairly well. Because a lot of times it looks like a very boilerplate, especially if you follow a practice of this is how we do it. Then actually generating code from that is a very straightforward exercise. And I have done it, and it does work actually pretty well. So what I wanted to talk about mostly is actually REST and the evolution of REST. As Joe covered HTTP a little bit, I'll go into a little bit different type of detail for it. By the way, REST has always been event-driven. If you look at what really is happening, an event comes in as a request and then a response is generated, and it has to be asynchronous. It's just how these things get tied together a lot of times makes them very synchronous in nature. So we'll talk about that a little bit. So as Joe pointed out, after RFC 821 came 1,791 RFCs later, you had 2616, which is HTTP 1.1. But before that, you had HTTP 1.0, and that was 2068. We don't really run much 1.0 out there. We really don't run also 0.9 out there much anymore, which it's so good that we don't. The first thing is that 1.0 and 0.9 required that you do a connect, you send a request, you get a response, and you disconnect, which meant that the active closing agent was actually the server. How many of you have lived through sort of the early years of the web where you had to actually increase the number of concurrent connections that you could allow because your kernel kept running out? That was because of HTTP. This is why I have dubbed HTTP as the worst protocol ever. It was designed really poorly. Now, there's nothing that says something that's been designed bad can't succeed. In fact, most of the times they do. You'd like it not to be that way, but a lot of times it is. So the success of the web was sort of in spite of the fact of how badly HTTP was designed. Another reason why it also wins my award for the worst protocol ever is that it is after all these protocols have been designed where they were using ASCII as the primary means of actually the grammar and everything that was there. Instead of going to a binary encoding, they went to ASCII. And they adopted all the worst practices that were already there in the effort to stay compatible. As I'll mention, HTTP2 and Speedy and all these, they get rid of that. They look at binary encoding instead. But take a look at what we have with this. We have a synchronous request response. A request, we can model that as an event going off. A response, and we can model that as an event as well. That's synchronous request and response. What happens in HTTP if you actually want to send multiple requests? HTTP 1.1. You send a request, you wait for the response, the entire response, and then you can send another one. This is basically, it lets you do bidirectional data. You can do a post followed by a get, or a get followed by a put, or a put followed by a delete, or these different operations. But you're bidirectional, but you can only go only one direction at a time. You can't mix them. And that's a problem, because then the behaviors that you can model are simply ones of send a request, do some action, get that response from it. Now, those can be two different events, but they're still tied to one another extremely tightly. They're correlated. And this was a problem. So, the great thing about standards is there are so many, right? And I didn't even put up here exactly which standards, these are just to protect the innocent. But, one might be something like, web services reliable messaging, for example. Request, an event comes in, it's acknowledged. That's usually at the sort of the underlying HTTP layer. And then the other side sends the response back. Now, this lets you have multiple outstanding requests and multiple responses. But at the situation of you can't be sending one, mixing them totally up unless they're on two different channels. And then if you go to the trouble of doing two different channels, why in the world are you using HTTP for all this? I mean, it doesn't make much sense, right? So that actually has been the evolution. So as HTTP didn't provide this, web services came along, and there was a certain set of standards that came out that basically let you do synchronous request and a synchronous response, but overall you could do a request response. You could kind of do this. So that was kind of painful. And as app integration really started to rise, they started to look at these things and actually really take a look at what they were doing. And as the web was kept going and kept going, a lot of the IETF, a lot of the protocol designers looked at a lot of this stuff and they said, wow, this is really messed up. What can we do? So one thing that they have started to do is they thought, let's actually see if we can run basic communication services over the web. And so two guys, Jonas Jacoby and John Fallows from Kazing, they approached when HTML5 was being standardized, and they saw this nice little sentence within the proposed HTML5 spec that said basically, to do, add TCP on web. And they thought about this, and they were like, you know what, I think we could do this. So what does this look like? So remember, you have to be backwards compatible to what is there. What that means is that you'd like to be able to have a fully asynchronous, bidirectional communication pipe over top of the web, but you can't break it. So how can you do this? Well, I had a little experience with not breaking the web, okay? There's something called the HTTP upgrade header, and it's how TLS can start. So you can go to port 80, have HTTP upgrade you to TLS, and then you're just talking TLS, and HTTP doesn't have any clue what's happening because it's gotten out of the way. So that's how WebSocket works, RFC 6455. You basically send an HTTP request, usually a GET. It has an upgrade header. It has some other things in it. And then what's returned is called a 101 switch. So it's a response code is 101, and you switch protocol. After that, HTTP goes out of the way. Now you can do whatever type of interaction you want. Traditionally, you would do something like streaming, where you would stream from backend servers all the way out to clients. You can do this without having any other type of interaction. But that is not the only trick. Oh no, this dog has a lot of tricks. So you can do ingest, where you actually turn this around, where you can actually just keep sending data directly in. And these are actually allow you then to build the idea of truly asynchronous request response on top of this. But WebSocket is just providing you with that channel. It's not telling you what the format of that is. So you have to build other protocols on top. But once you have this fully asynchronous bidirectional protocol, that is the transport protocol, you can actually run any type of protocol you want over top of it. That's kind of powerful, right? You can do a lot of different stuff over that. So that basically gives you full duplex asynchronous TCP over the web. That's kind of cool. That gives a lot of different options. But it hasn't stopped there. So, there's two sets of people within a standards a community. There's people who look at it and say, wow, it'd be great if we just looked at these things and we could progressively move them evolutionarily closer. Or you can actually just say, I don't really care about breaking stuff, I just want to make this work. And that's what has developed with Speedy. Speedy came out of Google, and it's also driven HTTP 2. And the idea here is that we don't want to be doing one direction at a time. We want to actually have a nice back and forth type of mechanism. So Speedy, among other things, has tried to address this by having channels and having framing. So instead of sending one request and getting back a stream of data for that request, you can send a request, which is small, and you can get back frames. And intermittently, you may get frames for other requests that you've sent in. So you've got a lot of control. This looks much more like this type of interaction, where you have request and response, but they're kind of tied to one another, and they can kind of come in a jumbled fashion. This gives you basically asynchronous requests and asynchronous responses. And this also is done and giving you full async request response over type of multiple streams of data at the same time, so that they can multiplex one another. But that's not all that has stopped there. How many of you have actually done web services or sent HTTP requests by hand? Just sending them anyway, apps or not. Okay. How many times have you seen your headers change that you've used, right? They don't change very often, right? And you may just send these over and over again. And it's actually one of the beauties of REST is that it's stateless, right? You send all the information and all the context that you'll need within that request in the form of the headers. But it's kind of really dumb to send all that data repetitively, right? So one of the things that Speedy has done is to do different methods of actually compressing that data, taking out redundant headers, doing all kinds of different things around that, as well as not sending them as text, if you can get away with it. So these are pretty good things. It also has a much more of a binary encoded feel to it. There's some definite performance improvements in it. And this is true of Speedy and HTTP 2. The track for HTTP 2 is within 6 months. It's pretty much going to be final, and there's already implementations that are starting to emerge. But they're not stopping there. WebSocket over HTTP 2. Now this is kind of the holy grail at that point. You basically can now mix in the fact that you have all kinds of different communication patterns with one another. So you could do asynchronous requests, you could do asynchronous responses. At the same time, you could be doing streaming and you could be doing ingest. Okay, so being able to do this totally asynchronously. This is why I talked about this being the evolution of REST. This is what we have. These protocols are getting defined, and being able to leverage them is something that we want to be able to do going forward. And this gives us basically a full duplex asynchronous with multiple channels and streams. This is really, really important. And the reason why it's important is because the scale of what we're going to have to do this with. As devices become much more prevalent, everything from Fitbits to the Nike Ups, Jawbones, a whole bunch of different, the world of different devices that we see. There is a set of different protocols and APIs that are developing. The ones that are easy are REST. They do have limitations, though. If you're using HTTP 1.1 type of style, you're in for potentially, really locking things down. Also, scaling issues. COPE. How many of you have heard of COPE? COPE's a REST-y type of model as well. A little bit lower footprint, but still has some scaling issues to deal with. It's becoming very popular, though. MQTT. MQTT is much more of a messaging-based way of looking at the world. Also, AMQP as well. So these fit really well for bringing and compressing messaging with a transport, which may or may not be a good thing, but it is something that is being looked at. WebSocket itself is also being seen as one way of handling certain types of ingest problems, especially as well as streaming problems, so that it fits really well there. SCADA protocols. All the different SCADA protocols that have been out there doing sensor capture for a long time, putting them into an Internet of Things type of world where now those sensors may be exposed, actually has a lot of problems. The first is most SCADA devices can't have more than one subscriber at a time. So you can't have multiple different devices or components listening to the same sensor. So that's a limitation. Or if you do, it is allowed, you have severe performance degradation of the sensor itself. That's a problem, right? So how to handle these types of things. These are different kind of communication patterns. And there's other types of SCADA stuff that's out there like DMP3 and a huge list of different legacy protocols to deal with. These are ones that that we will have to work with and see what evolves over time. But the good news is they're all event driven. Okay, so there is a consistent model that a developer can apply to all of these different things. Some of them blocking and they kind of suck, but it doesn't mean they won't win. So if you think about looking at everything as an event driven source, or thinking about it as an event driven problem, it does become a little simpler. So to that notion, it's been brought up a couple times about asynchronous message passing. And really what that is to do is it's trying to reduce the amount of shared state that is there, or that is actually shared mutable state, and how many are accessing it. So you want to actually pass messages around a shared state as opposed to actually making the shared state mutable by one another. So making that scale is not a simple thing. Asynchronous message passing is very closely tied to networking. Okay, if you're passing messages around, they're going to be over a network. You're going to have all the different things that you need to worry about. But you can think of them as asynchronous events. If you're thinking of them in that model, then it's much, much easier to scale. And it may sound flippant to say these things get easier, but they actually do. Once you start working with that model and not thinking about things as blocking calls, and thinking about asynchronous events, and thinking about your error handling as just another event, how it's being done. Maybe it's coming on a separate channel, out of band, but how it's being processed, it actually does simplify things. I'm very serious about that. So let's take a look at what a conceptual model, what we should have, for what this looks like. So I want to give, set some terms out here. A message. A message is what actually goes on the wire or is exchanged in memory between two components. The event is the sort of what's causing the state transition. In other words, that's the event that you're acting upon. Okay, and that gives us a little bit more of a definition. And we're not even talking about a response. We're talking about just that. That can be thought of as more like a fire and forget type of mechanism, right? We send an event, we don't care, and that's it. That is vastly different than how we have grown up, in doing development, where we're actually calling a function and getting a response and doing something with it. This is like a void, a function that returns void, right? It doesn't do, it doesn't return anything, but it has some side effect. And a lot of times that's what all asynchronous message passing systems kind of look like. Because the idea of waiting for a response is kind of, it looks stupid. It looks like it's inefficient, and it is. So think about things as much more of sending that piece of data, having it acted upon, something else happening, and potentially not getting back a response. But you can get back a response, but model it as a different event that is coming in. Don't tie it to one another. That's a very key thing. Once you break that connection, then the way that you view the world starts to change and how you would put there. And I'll go through a couple of examples here in a second. What this does is it lowers the coupling. Once you remove the fact that you've got a response at all, now you don't have a system that's coupled from the fact that it has to send a message and wait for something before it can continue. That's one key point. The second is that you do have coupling. You have a coupling from the fact that you have written something into memory. You've either put it into an area where something else can read it, or you've sent it on a network, and then the other side's picked it up. And so there's formatting around that, and there's all kinds of other laws that come into play. The contract or the binary contract comes into play. Those are still there. But breaking it so that it's not dependent on the return or the response. Very, very key. So in modeling errors as events, what has really done me well over the years is actually thinking about all errors as being asynchronous. They come in at any time, and they may manifest themselves as almost anything, okay? If you kind of think of them as, okay, non-corrupting errors. In other words, they're not going to corrupt you, but what they're going to do is they're going to actually be something you'll have to do something about, and that doing about may be just dropping it. At that point, you start to think about your error handling in a much different way. You know, as opposed to just listing out the number of checked exceptions you have to have in this function, you know, so that it will compile, you start thinking about, well, okay, what does it mean that, you know, I got an error, I got this type of error from a module? Maybe it's a version number I didn't anticipate or something like that. You start thinking about these things a little bit differently. Once you also do that, you start to be able to compose these a little bit better. It starts to make much more sense how you would break these things apart and actually get them to talk to one another if they follow certain contracts. And even if they don't have quite the same contract, you can make bridges where they do actually have the same contract on both sides. I'm not sure in law what that would be called. But all this kind of boils down to, you know, what a protocol looks like. And so the definition of a protocol I find very interesting. I kind of hate those talks that kind of give you a definition and then they go off on that, so I'm putting this at the end. But I think this is actually kind of important. You know, a protocol being a set of conventions governing the treatment and especially the formatting of data in an electronic communication system. That's our common definition, but it has two pieces there that are very important to us. One is formatting, okay, and that's sort of like the language. Then there's also the treatment, which isn't quite the same as, you know, as sort of grammar. It's much more of how we process these. What is the implication of all of that? And that is one of the things that, you know, when you talk to people who do protocol development, who design, they spend a lot of time thinking about what is the implication of the data that's in there and how should it be treated. And sometimes they put that in the standard or the, you know, the protocol spec, and sometimes it doesn't get in there. It's just sort of well known. But there's a second definition that actually is kind of important here, and that's, you know, the code, you know, prescribing strict adherence to correct etiquette and precedence. And this actually has a lot to do with how, you know, when you do this right, how systems are composable. Because if you understand the, you know, the strict adherence to the etiquette of what is going on, it also means that the systems are much more upgradable. They can kind of go along much better. And by thinking about a lot of that stuff up front, you make protocols a lot easier to guess. And if your connection in your contract is basically a binary contract and more of a protocol, then basically by thinking about that up front, you actually make things a lot more easily upgradable. And last thing is, you know, composability is all about protocol. Okay, and at this level, when you're talking about different systems and connecting them together over different types of transmission media, whether it be in memory or out of memory with a network or different types of networks, or even it could be carrier pitched, it really doesn't matter, right? You're communicating over some sort of media. And the composability of all of that is really dependent on that protocol. So thinking about those things and borrowing stuff from, you know, network protocol development, you know, I think applies. So I think with that, I'll leave it open for one or two questions. But, you know, these are all event-driven. And, you know, there really isn't anything special about it. You know, it's being done all over the place. We do it all the time. If we're doing development within a Java 2, you know, Java EE container, we're actually doing a lot of event-driven development. We just don't see it as such. Mixing in things like blocking calls and all kinds of other stuff around it, that may not be, you know, the best thing in the world, but we can get better at that, right? So that's it.
Thank you, Todd. That was awesome. I'm kind of bummed you didn't talk about ZMTP, the ZeroMQ protocol, when it came to all these beautiful asynchronous event-driven things, but okay.